Morning, students, or afternoon, or whatever time it is that you're seeing this. Today we're going to look at section 5.5, which involves counting techniques for probabilities. This lesson has quite a few new kind of concepts and some notation and things that are new as well. They're not difficult, just new, different. And I'm going to show you some calculator techniques also today. So make sure that you have your graphing calculator handy. If you have a non-graphing calculator only, that can probably work for you as well. I'm just going to be using the TI calculator here today. You could look on your own calculator's instructions if you're not using a Texas Instruments calculator. So grab your calculators, pause the videos, and get those handy because we'll be using those sooner rather than later. So specifically, when we're talking about counting techniques, we are talking about counting problems using the multiplication rule, which is simple. That's something that's new, not going to be new for you. Solving counting problems using permutations, solving counting problems using combinations, solving counting problems involving permutations with non-distinct items, and finally computing probabilities involving permutations and combinations. So we're talking about counting things, and probabilities are, simple. Our simplest probability rule is the probability of an event E is the number of times that E happens divided by the total number of possibilities. So it's favorable over possible. So, and sometimes it's not real simple to figure out the number of favorable outcomes. So when we're looking at the number of favorable outcomes as opposed to the number of total outcomes, we need sometimes to use permutations and combinations to come up with what those total numbers are. So let's start out by solving counting problems using the multiplication rule. This one is not new. This definition here is a little bit more complicated than it seems. This will make sense immediately when we see an example in a moment. But it says that if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R times ... different ways. Now, this is going to make a lot more sense in the context of a specific example like this one. A lunch menu has 2 choices for appetizer, 4 choices for entrees, and 2 dessert choices. So there is a total of 2 times 4 times 2. So we're just taking the number of distinct choices for each one, multiplying that together, and we have a total of 16 different meals that can be formed from that. So if we're walking through a cafeteria line and we can choose 3 choices for appetizers, 4 choices for main entree, and 6 choices for entree, and 5 choices for drinks, then that would give us a total of 360 different choices for that particular meal. So this is just counting the number of possible things that we have available to us by choices. Now this comes into play also, and you'll see some of these things in your homework. So if we had like the number of different ways a social security number can be chosen, for example. Like the social security number has 3 digits and then 2 digits and then 4 digits, right? So there are 10 ways that each of these things can be chosen, right? So 10 ways that each of these blanks can be chosen, which gives us a total of 3, 4, 5, 6, 7, 8, 9, 10 to the 9th different choices for social security numbers, right? So it kind of makes you wonder when that might run out, but they could pretty easily just change two of these things to alphabet, right? We made an alphanumeric, number instead of just a number, then we gain 10 to the 7th times 26 squared choices.
You're in the building.
Sorry for that interruption. 10 to the 7th times 26 squared. It gives us considerably more choices than we had just before. So these counting principles are a big part of knowing things. We could talk about this in the context of license plates and things like that. How many different possible license plates can we get if we use 3 letters and 4 numbers? So those are some things that could come into play there. So counting things is important. Now here's a new notation for us. The exclamation point in mathematics is called the factorial symbol. And n factorial is defined as n times n minus 1 times ... times 3 times 2 times 1. And let's stop right there because I want to put some context to what this means. So if we give n a number, 7 factorial is equal to 7 times 7 minus 1 times 5 times 4 times 3 times 2 times 1. Okay, so that's 7 factorial, and that is accounting. This notation is going to come into play. Now, there's two kind of exceptions to the rule or definitions that we have here. 0 factorial is defined to equal 1, and 1 factorial is also defined to equal 1. I'm not going to go into why that works, but it's going to be very important for you to just know that fact. All right. 0 factorial is 1, and 1 factorial is 1. All right, so let's have a look at solving counting problems using permutations. And permutations involve factorials, which is why we just had to define what that is. Permutation is an ordered arrangement. The key word here is ordered, right? It's ordered. Order is important. Whenever order is important, permutations are going to be used. So a permutation is an ordered arrangement in which R objects are taken from N distinct different objects, and repetition is not allowed. That's also another important fact. Repetition is not allowed. The symbol NPR represents the number of permutations of R objects selected from N objects. So permutation is an ordered arrangement. So if we put some, if we had this 2, how many ordered arrangements of 2 objects, of 2 things, can be chosen from 10? Okay. How many ordered arrangements of 2 objects can be taken from 10 is what that means. So this is the notation for that. And again, the criteria for when permutations are important. So we need the objects to be distinct, repetition not allowed, and order is important. If those 3 things are in effect, then we're going to use the permutation formula. The permutation of the permutation of R things chosen from N things is N factorial over N minus R. So if we just use that notation that we had just a moment ago, the permutation of 10 things taken 2 at a time, or 2 things from 10, the number of ordered arrangements, 2 things taken from 10 things is equal to 10 factorial, N factorial over, this was N and this was R, over N minus R factorial. And that's equal to 10 factorial over 8 factorial. Now, the neat things about factorials is that they cancel each other out. So if we have 10 factorial, that's 10 times 9 times 8 times 7 times, dot, 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 dot. It continues, right? 8 factorial is 8 times 7 times 6 times dot, 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 dot. Well, the 8 times 7 times the 8 factorials there will cancel out, and we're just left with 10 times 9, which is 90. So there are 90 different ways that you can choose 2 things from 10 distinct things when order is important. Okay, and no repetition is allowed. And that's how a permutation comes into play. Now, what does this look like in the context of a counting problem? Let's look at this example. In how many ways can horses in a 10-horse race finish first, second, and third? All right, so how many ways can a horses in a race, 10-horse race, finish first, second, and third? So we need to make sure that the conditions are met in this, and they are. The N objects are distinct, right? The 10 horses are individuals. Repetitions are not allowed. A horse can't finish first and second. Order is important. Order is important, right? Because we're talking about first place, second place, third place. That makes order important. So all the conditions are met, and so what we're looking at here is a permutation of 10 objects taken 3 at a time, and that's found by 10 factorial over 10 minus 3 factorial, which is 7 factorial. And again, 10 factorial is 10 times 9 times 8 times 7 times 6, etc. And then 7 factorials there. And so the 7 factorials cancel, and we're left with 10 times 9 times 8, or 720 different ways that horses can finish first, second, and third in a 10-horse race. All right, so if we were talking about a probability here, what's the probability that my pick for first, second, third is correct? And it's 1 out of 720. So you have a 1 out of 720 chance of just randomly picking the order of 3 horses in a 10-horse race. All right, so that's where it's going to come into play with probabilities. Now, solving counting problems using combinations. A combination is another counting technique, and the combination is a collection without regard to order. In other words, order is not important. If we just wanted to know the number of ways we could choose 3 horses from 10 horses, then this becomes a combination instead of a permutation, because the order is not important. Okay, so without regard to order, n distinct objects without repetition, the symbol NCR represents the number of combinations of n distinct objects taken R at a time. And here's the formula for that. Okay, the number of different arrangements of R chosen from n objects in which the n objects are distinct. Okay, so here are the conditions for a combination. The n objects are distinct, same as permutation. Repetition is not allowed, same as permutation. But in combinations, the order is not important. Okay, so the important difference between combinations and permutations is that the order is important with permutations. With combinations, the order is not important. Okay, so the formula is n objects taken R at a time. Combination of that is n factorial over R factorial times n minus R factorial. All right, so if we look at that, we're going to look at this example. How many different simple random samples of size 4 can be taken of a population whose size is 20? Now, if we give this a little meaning, a little bit more meaning, if we had a class of 20 people and we needed to choose 4 people, how many different ways can 4 people be chosen from 20 people? How many different groups of 4 could we choose? All right, so if we look at the individuals are distinct, the number of sample size is 4 from a population of size 20 is a combination, and the reason it's a combination is not a permutation is because the order in which the individual is selected is unimportant. It doesn't matter. Okay, we're not talking about finishing a race first, second, or third. We're talking about just plain old choosing 4 people from a population of 20. All right, so using the formula, we have a combination of 20 people taking 20 things taken 4 at a time is 20 factorial over 4 factorial times 20 minus 4 factorial. And so that gives us, again, we can see how the combination of the factorials will cancel themselves out. 20 factorial is 20 times 19 times 18 times 17 times 16 times 15, etc., which is 16 factorial. And then over 4 times 3 times 2 times 1 times 16 factorial. So the 16 factorials cancel out, and we are left with that. Now you could do some cross-canceling here if you wanted to. 4 goes into 20 5 times. 3 goes into 18 6 times. The 2 is just going to be left there. So that can give you some different things to work with. So if you were just using this. Now, I think that now is probably a good time to talk about the calculator. So let me swap over here and show you where you can find these operations on your calculator. So if you would get your calculators out. And again, I apologize. I know some of you may have different editions of your calculator, different calculator editions than this one. So this could be a little bit complicated for you, but you can do this. We want to go to the math key. Okay, so if you press the math key, then go over, page over across to, scroll right to probabilities. And then once you get to probabilities, you're going to see combinations and permutations right there, number 2 and 3. Now, incidentally, over in chapter 7, which we're going to do next, I think chapter 6, we're going to be using these things a lot. Okay, so, and also in this section, you find the, that's where you get the symbol from. Now, I haven't looked carefully through all of the shortcut keys and things here, but I don't think that you're going to find the factorial symbol anywhere except for under the math button, okay, and then the probability button. So it's going to be important that you know math again, and then scroll right over to probability, and then you can choose choice 3. If you press the number 3, and then you're going to get NCR. Now, here's the way you have to do this, I think, and let me just kind of scroll through this. We have to do, if you hit enter here, it's going to give you a syntax error, of course, and because we didn't put any numbers in to do this. So here's the process of doing this. I'm going to quit and just get back to the home screen, and I want to do 10 things, math, and go over to probability, and let's do a permutation, number 2, 10 things, 3, and hit enter, and we get 720. So that was the answer to the first problem. We had 720 ways that the 3 horses could finish first place. And the other one that we did was 20 things, right? And we did a combination there. So if we go over to probability again, and we do a combination of 20 things, taken 4 at a time, and we get 4,845. So this notation is going to be very helpful to you. You don't have to do the tedious arithmetic that's involved with combinations and permutations if you use the math probability feature on your TI calculator or others. Now, a different calculator may have a little bit different syntax, but this is how the calculators that we're going to use work. So again, you have to put the number in the population. Let's do another one. Let's do, if we had if we wanted to know the number of ways we could choose 10 things from 50 things, we can do a combination. 50 things chosen 10 at a time, and we can do that. That's a very large number. Scientific notation there. Then that's kind of important. So combinations and permutations are going to be with us for the rest of the semester, so it's kind of important to get used to doing those. Now, if we want to solve counting problems involving permutations with non-distinct items, this is a different formula. We'll have to do this one by hand, but it's not complicated. If I could get my slideshow to advance, I've got to give me just a second here. I've got to get back off the calculator and into the screen, and then we're good. So the number of permutations of n objects of which n1 are of one kind, n2 are of a second kind, nk are of a kth kind is given by n factorial over n1 factorial times n2 factorial times, and this L doesn't mean anything. It's supposed to be dot, dot, dot there, all the way down to n sub k factorial, where n, the number of total items, is equal to the sum of the different kinds of items. Now, this formula is complicated looking, but it's really quite simple to look at. So we're talking about non-distinct items of a different kind. All right, so here's an example of that. We have a bag of 20 M&Ms. 5 are yellow, 5 are green, 6 are blue, and 4 are brown. So there's 20 total objects of different kinds. They're non-distinct items because they're all M&Ms. All right, so let's have a look at an example of this. How many different vertical arrangements are there of 10 flags? So 10 flags. If 5 are white, 3 are blue, and 2 are red. So let's go back to the formula that we just looked at. If we take this formula, it's n factorial times all the different types underneath it. So in this case, we have 10 flags, so the number of different arrangements is going to be n factorial, which is 10 factorial, over 5 factorial times 3 factorial times 2 factorial, where those are the distinct different kinds of things that we're looking at. Okay, so you're going to have 10 times 9 times 8 times 6 times 5 factorial. The 5 factorials will cancel. 3 factorials, 3 times 2 times 1, which is actually 6. So the 6 factorial cancels with the 6. Excuse me, the 3 factorial cancels with the 6. 2 factorial is 2 times 1, which is 2. So you could cancel that with the 10 and get 5. And then you've got 5 times 9 times 8 times 7. 2,520 different vertical arrangements could be made that are distinct by color. So that's just an example of something like that. So if anytime you have different arrangements of different types of things, then that's the formula that we're going to use. Okay. Now, as we finish up this, we have computing probabilities involving permutations and combinations. We're almost done. And the Illinois lottery, an urn contains balls numbered 1 to 52. From this urn, 6 balls are randomly chosen without replacement. For a $1 bet, a player chooses 2 sets of 6 numbers. To win, all 6 numbers must match those chosen from the urn. The order in which the balls were selected does not matter. So immediately we were told that the order doesn't matter, so we know we're going to be using combinations here and not permutations. And so what we need to know is how many possible combinations there are of drawing 6 things from 52, and then we need to know how many favorable ones. So we have the total number without regard to order is the number of combinations that we have. 52 things taken 6 at a time. All right, that's the total number of possible combinations of 52 objects taken 6 at a time. Okay, and how many? This gives us the size of the sample space. And again, this would be a calculator thing. You would put this in your calculator. Actually, let's do it. Let's just make sure that y'all remember how to do that. So 52 objects taken to 6 at a time. Let me see, I need to get out of this editing mode and switch over to the other screen. So 52 objects. Move my mouse. $52 objects. We need a combination, which is under math, probability, 3. Taken 6 at a time, not 66. There's my delete button right there. Start over. 52. Chosen 6 at a time. Enter. 20,358, 520. And that's what we had in the other way. So there's 20,358 possible ways that a winning lottery ticket can be chosen. And each dollar ticket gets you 2 tickets. So there's 2 choices or 2 possible winning victories out of 20,358. 20,358,520. Sorry, I'm not reading that correctly the first time. That's about a 1 in 10,000 chance of winning the Illinois lottery. So that's how you can use those counting techniques to do this. So your homework from this section is page 283, and the problems are listed there. You can upload those into PowerSchool when you're done. And if you have any questions, always ask. Thanks. Have a great day.